So I'll first read the slide and then I'll make some verbal comments. So I first met him in 1963, which means that of everyone here, except of course for John, I'm the one who has known him the longest, or at least worked with him the longest, right? So I was teaching at Stanford, but then I decided to go back to India. I didn't actually have a job, and I remember I was Xeroxing papers at Stanford to take back with me to India. And Dana Scott came over and said, Rohit, you don't need to do that. When you need a paper, just write to me and I'll send you the paper. What Dana didn't tell me was that he never responded to letters. So, but things worked out. So Kreisel had got both John and I interested in natural well orderings. Now, there is the Church Kleene omega 1, which is, of course, smaller than Aleph 1, which is the same as omega 1. And it's essentially the first ordinal for which there is no recursive relation which expresses that ordinal, right? And now, which are the natural ones? So it's easy to think of natural orderings for omega squared. You have an ordering on omega, which is the one we are born with, and then you just take pairs and order them in the natural way. For omega to the omega, you order sets in a certain way. But what about the general case? We didn't solve this problem, but we did publish an abstract to the JSL. And here is the abstract. So this is, I guess, the very first thing that I published with anybody, and perhaps it's the very first thing that John published. So an isomorphism recursive well orderings. Now, there was an idea that there could be some hierarchy for recursive functions which were similar to the Kleene hierarchy for hyperarithmetic sets, right? And my advisor, who was Hartley Rogers, suggested to me that I think about that, about how to come up with a hierarchy, right? Then I came across a paper of Kreisel's in which Kreisel showed essentially that any such a hierarchy was logically impossible. I saw some of the problems that Kreisel had raised, and so that became my dissertation and not the question that Hartley Rogers had posed for me, right? But still, Kreisel was interested in the issue of natural well orderings, and he got both John and I interested in that. So here is our theorem. So let A and B recursive well orderings of the same ordinal gamma. And under what circumstances are they recursively isomorphic, right? Now, one had thought that the larger the ordinals, the greater the computing power, but this didn't work out because John Myhill had shown that for any arbitrary power that any recursive well ordering had, there was another ordering of size omega, which had the same computing power. So Myhill essentially destroyed Hartley Rogers' idea. But nonetheless, the question of natural well ordering remained. And so this is the theorem that if you have two recursive well orderings of the same ordinal, then when are they recursively isomorphic? And then it depends on whether certain functions are recursive. So if multiplication and addition are recursively presentable, then a gamma can go as far up as omega to the omega to the omega. And if exponentiation and successor are recursively representable, then you can go up as to the first infinite epsilon number. Now, here is a result of Kreisel, which is stated in here, but actually there is no result here because Kreisel starts by saying every ordinal less than gamma, 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 and then there is no conclusion. And I think that we just goofed on that one. So then after that, I went back to India. As I said, I didn't have a job, but I did have a mother. And so I stayed with her for free. And eventually I didn't get a job teaching at Punjab University. So eventually there was a paper by Crossley and Kister in which I did not participate. This is the paper on natural well orderings, Archiv für mathematische Logik und Grundlagenforschung, and appeared in 1987, which is 24 years after John's and I's abstract. Okay, so I met John for the first time at Oxford, right, when I was going back to India. Things didn't work out for me in India. Basically, I was essentially the only mathematical logician in India. There was nobody to talk to, and the Indian government was incredibly bureaucratic, so that keeping contacts with other outside people outside India was difficult. In fact, when I went back to India, I knew the law was that I had to close all my foreign accounts before I entered India. And so how was I to pay for the American Math Society and Association of Symbolic Logic? So I gave $500 to Chrysler, and every time that the renewal came up, I wrote to Chrysler, and Chrysler religiously paid those subscriptions. So there were some ways in which Chrysler was very reliable, maybe in others not so reliable. So things didn't work out in India. And so I went back, and it was Chrysler who found me a job at Bristol, and Shepardson was there. And of course, Shepardson was part of the early group of Rabin, Scott, Anil, Kleene, and so on and so forth, proving results about finite automata. So I taught at Bristol for 2 years. I had a car, and so I often visited John. And I remember on one occasion, my car smashed into John's garage door. And John just smiled at me and said, you were drinking too much, weren't you? And I was afraid that John would ask me to pay for the garage door because my salary at Bristol was only $3,000. And I didn't think I would have money to pay for the garage door. But John said nothing, right? I mean, his good nature has been there ever since I've known him. Okay, so after that, I met John a couple of times. I went to Australia and I met him at Monash University. It was summer here and it was winter there, and I was incredibly cold, right? And after that, John came to India for a conference which I had started, and my wife Carol met him, and we had some nice times together. Okay, so much about John. I will now proceed to what I want to talk about. So abstract for logic and rationality. So logic aims at truth, or more accurately, at deriving some truths from other truths. Of course, Russell disagrees with that because he says that logic has nothing to do with truth. We assume certain things and we derive certain other things, and we don't care whether they're true or not. But in real life, we tend to want to derive some truths from some other truths. So why are we interested in truth in the first place? And surely one reason is that relying on truth makes it easier to make better choices. So one could think of game theory as a tool which bridges the gap between logic and rationality. So decision theory or single agent game theory tells us when to make the best choice in a game of us against nature. But nature has no desire to further or frustrate our efforts. Things change when there are other agents involved. Then they may try to help us or may try to hurt us. So what the best thing for us to do will depend on what they do. And of course, they will think the same, that the best thing for them to do depends on what we do. So issues like common knowledge and rationality, rationalizability, then arise. So let me allow myself to make comments. Okay, so common knowledge and rationalizability will then arise. And I don't know how many people here are interested in common knowledge, and even fewer probably on rationalizability. Maybe I'll say something about that. I think common knowledge is much more important. Okay. Now, each of us carries with us an envelope of beliefs, just as a tortoise carries its shell. Working with others, even when we have compatible ends, requires reconciling our respective shells, right? Now, a person that I want to mention in this context is a Baltic German researcher, I think maybe Wixkull, who actually studied the shells, not only of human beings, in which he was not all that interested, but he was much more interested in what kinds of shells animals have. So one could say some of you might be aware of this paper of Nagel's on what it is like to be a bat, right? But Uexküll anticipated Nagel by maybe 50 years. So when we are working with others, even we have compatible ends requires reconciling our respective shells. So perhaps I have my shell and I'm inside that shell, and then somebody else has this shell in which they live. And then this is the part that we have in common, and we have to somehow manage to work together in that part that we have in common. And this is a fact that's not commonly understood, because we all think we live in the real world. There is a real world that science studies, and we don't realize that actually we don't live in the same real world. We live in different real worlds, and we have trouble reconciling my world with yours. So about the shells, how different is she from me? That will depend on whether we are choosing a movie to go to, or whether we are choosing whether to vote Democrat or Republican. We may agree on the movie and not agree on the party. So then we can define a logical distance between two people in areas in which they can collaborate, and other areas where they will see each other as opponents, if not as enemies. So the resulting metric space or collection of metric spaces can be a subject of mathematical investigation. And I will come to that metric space later on. So for example, consider people who refuse to be vaccinated because they feel that vaccination is dangerous. We may reproach them and try to convince them of the error of their beliefs. Now, I myself have been vaccinated twice and also boosted twice. But at the same time, if other people refuse to be vaccinated, I will keep my distance from them. But at the same time, I don't get mad at them, because I just think they have some false beliefs. They're acting on their beliefs, and I have no right to judge them. I have a right to be careful with them. I don't want to be in the same room with them, but I don't judge them. So if their belief is sincere, we will be more charitable. These points about the connection between knowledge and obligation are spelled out in a paper with Parikh and Kogan. Parikh he's a professor at University of Maryland, he's a former student of mine, and Eva Kogan, she's a colleague of mine at Brooklyn College, and she's just retired. So here is a quote from Van Rooij, who is now the director of ILLC. So this is a big job and a high honor, which I'm sure but I remember that before he was director, we had an amusing meeting, because I was staying at a hotel as a guest of ILLC, and I invited Van Rooij to come and have lunch with me, and at a nearby restaurant. So after the meal was over, I wanted to pay for the lunch. And he said, why? And I said, you cycled here in the rain, because the Dutch don't think anything of cycling in the rain. And he said, all right, but the next time I'll pay for lunch and you cycle in the rain. So this is an introduction by him. And essentially, he's interested in the question of why do we ask certain questions and what do we gain by asking these questions. It's a very important, interesting paper. And I would heartily recommend his work. Okay, so it says a decision under strict uncertainty and ordinal preferences, the decision problem can be modeled by a triple like T, E greater than or equal to, where T is the set of states that the agent thinks are possible, representing her beliefs. E is the set of alternative actions that she considers, and there is a partial order on state action pairs, namely, this is subset of T cross E. In other words, if T cross T, comma E is better than T prime, comma E prime, which means that in situation that E chosen in T is better than E prime chosen in T prime. And we can test the preferences by asking people to choose. So he says, I will take the actions in set E to be primitive, and whenever agent can represent a preferences by cardinal utility function, the ordinal is replaced by U, a utility function from state action pairs to real numbers, when the agent can qualify her uncertainty. The problem is starkly called a decision with risk. So decision under uncertainty means that you don't have any probabilities whatsoever. You just may have some idea, this is likely, this is unlikely, and that's it. When you have a decision under risk, then you have probabilities for every event. They may be subjective, but you do have them. Okay. So given two actions, E prime, and a set of states, we define E prime is better than E given A if for every T which satisfies A, ET is not as good as E prime T. This is T prime. Okay, so if A is a formula, we'll identify it with a set of states which satisfy A. So E less than or equal to E prime means if I know E, then E prime is at least as good as E. So I may not know what the situation is, except that I know the fact A, and then I can say, well, given that I know A, E prime is at least as good as E, so there is no reason to use E. Okay, if B implies A and E is better than E prime given B, then E is better than E prime, E is worse than E prime given B, then E is worse than E prime given A. And a maximal action is one which is better than any other action. Such actions may not always exist. Okay, now if A is maximal given A and B implies E, A, then E is also maximal. All right, so when we choose an action, we prefer to choose a maximal action, and learning more makes it easier to find a maximal action. Okay, so now we see a connection between logic and rationality, that when we have logic, then we derive certain facts. Having derived certain facts, then we are better able to choose. Okay, now order versus utility, roulette lotteries. So suppose that Sona, this is one of my granddaughters. My granddaughters often appear in these things. She prefers chocolate to vanilla and vanilla to strawberry. Then we know that her ordering is C better than B better than S. But we do not know if your utilities are 10, 9, and 1, in which case vanilla is almost as good as chocolate, or they are 10 to 1, in which case vanilla is not much better than strawberry. So if we just ask her, which do you prefer, chocolate, vanilla, strawberry, then we can not tell whether it's this or that. So we can offer her a choice. She can just pick vanilla, or we toss a coin, and if it lands head, she gets chocolate. If it lands tail, she gets strawberry. So she can get vanilla or a 50-50 chocolate strawberry. Okay, if she picks A, then this is more likely. And if she picks B, then this is more likely. And now, since Anil has introduced us to a relaxed manner of speaking, let me give you a story from Amartya Sen, whom some of us have met, and I certainly have met him a couple of times. Probably Anil has met, since Anil has met everybody. So he says, suppose you go to somebody's house and you have dinner there, and then that person offers you a beer. And the choice is beer or go home. Since you like beer, you're inclined to choose the beer. And then says, wait a minute, it isn't just beer. I can also offer you to snort some cocaine. So the choice is beer, cocaine, and go home. And now Sen points out that the original choice with beer and home is still present. Beer is still available. So you still have the same two choices, beer and home. And the fact that cocaine is added shouldn't make you prefer go home to beer, right? But it does. So Sen's point is that having the choices can make you feel differently. Okay, I said that I might be the only person who knows Amartya Sen, but I see that Ali Khan is here, and Ali Khan, I'm sure, knows Amartya Sen very well. Okay. Now, horse lotteries are introduced, at least in a paper by Anscombe and Aumann. Aumann, as some of you might be aware, is a Nobel Prize winner, and he won his Nobel Prize in 2005, the same year as Sheldon. So in addition, the kinds of lottery that I was talking about, where you toss a coin, right, where it is sort of common understanding that if it's, unless the coin is suspicious, heads and tails are 50-50. But Arman Anscombe introduced another kind of lottery. Suppose there are three horses running, Baroda, Medina, and Donegal. So Baroda and Medina are cities, of course, and Donegal is an abbreviated name of another horse in another race. So suppose we offer her a choice. Either she just gets vanilla, or the other choice is if Baroda wins, she gets chocolate. If Medina wins, she gets vanilla. And if Donegal wins, she gets strawberry. So she has to choose either vanilla outright, or she can choose this. Whether she picks C or D will depend not only on her preferences in ice creams, but also her opinions of the horses. So that's why they call them horse lotteries. Okay, so in the following, we'll focus on roulette lotteries and the probabilities will be objective, but horse lotteries are important because bringing in this horse lotteries allows Alvin and Anscombe to say something about both which do you prefer, chocolate and vanilla, and which do you think is likely, Medina or Donegal. Okay. So suppose that the ordering is created by utility, which has numbers. So ET is better than E prime T prime if the utility is better. And then we can define the worst outcome of an action, E, as the worst thing that can happen if you choose E. So the minimum utility with all possible T's, and we can define the action with the best utility to be E star, so that the security of E star is more than the security of anything else. So the security of E is the least security of any other E. And if B implies E, then SB is at least as great as SAE. So here's an example in the following matrix. Even E2, there are three actions, even E2, E3, and there are three states of nature, T1, T2, T3. And so if in state T1, you do action E1, your payoff is 4. Now, you can see that in this situation, the security level of E3 is 2. The others have the possibility of 0, so they both have security level only 0, and so E3 is the best. However, suppose we find out that T3 is not in the running. So in that case, you can see that now the security level of E1 is 4, and the security level of E3 is still only 2, and so E1 becomes the winner. If I know T3, then E1 is the winner. So the security level always rises when we learn something. And for the minimum over a smaller set is always as great as the minimum over a larger set. Now, so two agents with the same utility, here they have the same utility, but different information can differ on which is the safest action. If the actual T is T1, one agent knows that it's not T2 and another is not T3, then they will disagree. If it's not T3, then of course E1 is the best. If it's not T2, then E1 is no longer the best because it's got to 0, and therefore E3 becomes the best. So they will disagree on the best action, even if they have the same preferences, but different utilities. And I don't want to bring in politics, but I would say that a lot of the political discussions about what's going on in Ukraine between Biden and Putin and Zelensky has to do with their having different information and perhaps having the same utility. Maybe they have different utilities also. Okay, if in addition to the utility function U on such pairs, we have a probability P defined on sets of states, then we can define an expected value for an action. So expected value of A given X is sigma ui of WA PW divided PX, where W ranges over all states which satisfy X. Unfortunately, the expected value does not necessarily increase when we know more. So the safety always increases when we know more, but the expected value may go up or down. And the reason your expected value might go down is because some things that we really liked turn out not to be possible. And so say, for example, you're going to propose to a beautiful woman, and if she says yes, the expected value is 1,000, and if she says no, the expected value is 0. And then you find that she only likes men who are 6 feet tall, and you're only 5'7", then your expected value, the probability of her saying yes drops, even though the value of her is still 1,000. So expected value goes down. So knowing more is not necessarily an advantage if other players are involved and they know that you know more. So here's an example. Two individuals, I and J, are to predict whether the top card of a shuffled deck is black or red. The predictions are made in sequence. I guesses first, and then J after hearing I's guess. So if they make this, so the rules are, if they make the same prediction, each wins €1, whether the prediction turns out correct or not. If they disagree, then the one who is correct wins 3 and the other nothing. So if they agree, then it's 1 and 1, regardless of whether they're right or not. If they disagree, then the correct one gets 3 and the other one gets nothing. Okay, since I has no basis for preferring one or the other color, he'll choose at random. Then J will choose the opposite color. So I may be right and J wrong, or I may be wrong and J may be right. And so one of them gets 3 and the other one gets 0. And so the expected value is 1.5. But now suppose someone offers without charge an arrangement whereby the first player is told the actual color of the top and he makes his prediction. Then the parties would be unanimous in rejecting that arrangement. Why? Because I is getting some information. He gets to know what the color is. But with that information, he would choose the correct color. J would then make the same choice, and they would each gain only €1 rather than expected value 1.5. And there is a wonderful quote from Napoleon, and this appears in Bernard Shaw. And this one is about Napoleon. Okay. So somebody sends Napoleon a letter which perhaps contains information that his wife Josephine has been unfaithful. So a woman who is a friend of Josephine tries to steal that letter before Napoleon gets to read it. So okay, so Josephine has perhaps been unfaithful to Napoleon. There is a letter saying something about that, and this friend of Napoleon, also a beautiful woman, tries to steal that letter before Napoleon can read it. And then Napoleon says, a letter about a woman's unfaithfulness should never be sent to the husband because the husband would not read it. Because what man wants to fight a duel, cause a scandal, and so on and so forth, when he can save himself all this trouble by not reading the letter? So it seems like Napoleon anticipated this problem that Van Rooy is pointing to. Okay. However, if I stole the color of the top card and J is not aware, then I will choose the right color, J will choose the opposite color, and their payoffs will be 3 and 0. So I loses by knowing the correct color, but only if J knows that I knows. This again is very, very relevant to most political discussions. Okay, now whether a particular action is good or bad depends on what we believe. If we believe that a glass of wine is poisonous, then we won't drink it. When more than one agent is involved, they're considering a pair of actions. They will want the pair to be good for both of them. Otherwise, one of them will opt out. So if several pairs of actions are good, then they will want a pair which is Pareto optimal, in a sense which I'll define. They may also want the benefit to be as good for each as possible, and following Nash will define the notion of Nash optimality. Now, Ali Khan, who is present here, is a well-known economist, and I wanted to ask him whether the notion of fairness coming out of Nash bargaining has been mentioned before, because it's obvious that Nash is thinking of fairness, but I don't know whether he uses the word fairness in his paper. You don't know.
I know, but there has been extension where he has been interpreted to be fair. So there are these other solution concepts, extension of Nash solution concepts, where
Right.
fairness is made prominent. The Kalai, Smoridinsky, etc., etc. But
Yes.
I'm just pointing to papers. I don't know them.
Well, since you mentioned Kalai and Smorodinsky, I will mention a story about one of my students. So Nash defined an equilibrium. You know, two people are bargaining, and Nash says, what is the bargain they should arrive at? And he actually proves a precise theorem. Then there is one condition that he imposed, which was much criticized, and Kalai and Smorodinsky came up with a different definition for what the bargain should be, and the two of them don't usually agree. So in an exam that I gave in a course on game theory, I gave the students a particular problem, and I asked them to calculate the Nash bargain and also the Kalai-Smorodinsky bargain. But unfortunately, I didn't check the solution. So when I went over the problem in class, I discovered that the two solutions were the same for this case. Okay, so let me just say, the same for the question that I raised, right? I was surprised because, of course, the two solutions are in general different. So I wrote to Nash about it, asking whether he knew necessary or sufficient conditions about when the two solutions would be the same. And Nash wrote back saying that they would be the same if the problem was symmetric. But this was obvious that the problems would be, that the solutions would be the same. But so it didn't tell me about the solution, but it did tell me that Nash didn't know the necessary and sufficient conditions. And if Nash didn't know, probably nobody knew. And a student of mine, Todd Stambo, solved the problem. Found necessary and sufficient. So if agents have different beliefs, then a pair of actions considered good by one may be considered bad by the other, or simply not good enough. So some form of dialogue will then become necessary to resolve the difference in beliefs. The beliefs do not need to coincide for us to agree on a pair of actions. If we are choosing among several movies, then our difference in views between baseball and cricket, no matter how large, may not be an obstacle. Okay, beliefs are expressed in language. So suppose that you and I share some language. X is the set of my beliefs in L, Y is the set of your beliefs in L, Z equals X intersect Y is our common ground. And when discussing with you, I'm entitled to use members of Z and also members of X, which I've convinced you of. I may also convince you to remove members of Y whose falsity I convinced you of. I may not use elements P in X such that not P is in Y unless I've convinced you of P. And a very important figure here is Dung. He's Vietnamese, but teaches Bangkok. I don't know why, I've never met him. So his paper on artificial intelligence has been very influential. He talks about dialogue and when I can disprove something you think and so on and so on. And there's a whole school now that has arisen from that. Okay. So now as we shall see, whether a particular action is good or bad will depend on our beliefs, and we'll investigate the connection between beliefs and judgments about actions. So suppose one of us, say you, does an action A, which has utilities for both of us, F80 for me, G80 for you. The action is acceptable if the expected values of FA and G are both positive. In other words, your action will benefit you and benefit me. It's strongly acceptable if it's acceptable, and as with Nash bargaining, the product of FA and GA is maximized relative to other possible actions of yours. So these notions are relative beliefs. Suppose that my total beliefs amount to some set of beliefs X and yours to Y. So take the belief words that satisfy X. I'm only going to consider these and I will average over that set. On the other hand, you might average over a different set. And so an action that looks good to you may look bad to me, or vice versa. Okay, now I consider a single action done by just one of us, but perhaps it is a pair of actions which we can jointly perform. For instance, in the Bach-Stravinsky game, either both listen to Bach or both to Stravinsky. The case where one listens to Bach and the other to Stravinsky has zero payoffs because they want to go to the same concert together. So very often people will only consider this and that, and they will not even try one of these. So if there are two players and there is a finite set space of possible states and a finite set A of possible actions, P is the probability, then expected value of a pair of actions UIAB is U1XAB and U2XAB. So we'll be interested in those cases where A is a formula in our language and XA is a set of words satisfying A. And I'll just write UI bar of AAB. So whether A is a set or a formula doesn't matter because the formula can be identified with a, okay. So the consequences of ABA are utility for me and utility for you. Okay, so here is an example. Anne is suggesting going to the movie A Day at the Races at the movie theater Roxy. The usual ticket price is $15 per person, and cost-conscious Bob says it's too expensive. Anne responds with, today is Thursday, and they have a 50% discount on Thursdays. So her remark reduces the total expected cost from 30 to 15. So information entered and the cost went down. So suppose Bob responds with B, you are right about the rule, but today is actually a Friday and there is no discount. So they have a disagreement about which formula is true and hence the expected cost. If it's Friday, then $30. If it's Thursday, then $15. Okay. Now the dispute can be resolved by simply consulting the calendar. Suppose that Anne finds the calendar and shows Bob that it's not Friday, but Thursday. So Bob replaces his formula B by A and they agree on the expected cost. Now note that the conflict was resolved because Bob already had the belief the calendar is correct. In other words, Anne was relying on a pre-existing belief of Bob. Bob had agreed that the calendar is correct and derived from that today is Thursday. Second one, Bob is buying a car and the salesman offers a model which Bob likes, but it's for $35,000. Bob is uneasy about the price and that the salesman says, this model is very reliable and we have very few repair costs. In fact, for only $500, we'll cover all repair costs for the next 10 years. So Bob decides to buy the car as the sentence uttered by the salesman reduces the expected cost over 10 years. The value of the car to Bob is now more than $35,000. So there was certain value from having the car, and now there is the additional value of not having the cost of repairs. Okay. Suppose that Anne and Bob have pairs of actions, A1, B1, A and BM, available to them and discussing which pair to perform. Both go to Bach, both go to Stravinsky, or stay home. So the expected benefits for them can be written C1, C1 prime, CM, CM prime, but these first are the benefits to Anne and the second are the benefits to Bob. We'll assume that all these are positive because otherwise why bother? Okay, now we'll consider a single belief case where they have the same beliefs and let X be the conjunction of their common beliefs, then we might as well think that W, the set of words, is simply the set of words which satisfy their common beliefs. And we now define the notions of Pareto optimality and Nash optimality. So a pair of actions AB is Pareto optimal if there is no other pair CD which has consequences for each of Anne and Bob, which are just as good as AB for both of them and strictly better for one of them. So AB is Pareto optimal if there is no way to do better. And it's Nash optimal if there is no other pair which has a greater product. Okay, now a Pareto optimal pair need not be Nash optimal. For instance, if $100 are divided between Anne and Bob, Anne gets 99 and Bob gets 1, then this division is Pareto optimal. Why? Because if we do 98 and 2, then Anne is losing out. Pareto optimal means nobody should lose. So it's Pareto optimal, but Anne would suffer with another division, 98 for her and 2 for Bob. But it's not Nash optimal because each getting 50 would give the higher product of 2,500. Now, I don't know whether John Rawls was aware of this work of Nash. Because, of course, his theory of justice is a very important contribution to the theory of fairness. Okay. But Nash optimal does imply Pareto optimal. Because suppose U prime are Nash optimal, but not Pareto optimal, then there must be VV prime such that U is less than or equal to V and U prime is strictly less than V prime, but then this product is less than U prime V prime, and UV was not Nash optimal. So Nash optimal is a stronger property than Pareto optimal. Okay. Nash used a convexity argument to prove the existence uniqueness of a Nash optimal point. We, on the other hand, using the finiteness. If you have a finite number of pairs of actions, then there must be one which is Nash optimal. But they may have different beliefs, and some CI evaluated by one set of beliefs might be positive, while it's negative by another set of beliefs. Okay. So many belief cases will arise when they don't have the same beliefs. So suppose they have different beliefs, X for N and Y for Bob, and in that case, the notions of Pareto optimality and Nash optimality will come in two flavors, right? Conflicts will arise when one party tries to convince the other party of the wrongness of their beliefs. And one way one can convince the other is when beliefs of one or the other party are not consistent as a set. Suppose that Anne said X is not consistent. When a question comes up to her, she uses a consistent subset X prime contained in X to solve it. This is something that we all do. We have an inconsistent, our beliefs are not consistent as a global set, but then when a question comes up, we pick some subset, use it to arrive at a conclusion, and if somebody raises a problem, we just become angry. So suppose now that Anne has a belief A and Bob has a belief B, which is incompatible. So Bob will then can point to a set X prime contained in X, which is set of Anne's beliefs, and X prime implies not A. Anne will then be compelled to withdraw A and may agree to go along with B. So Bob's acceptance of the calendar as an authority was such an example. It was Bob who was inconsistent, and such themes have been developed by Dung, Amgud, and others, and the details will be included in future versions of this paper. So since I have a little bit of time, I will at this point tell a story of Robert Aumann. Okay, so there was a conference on game theory at the Taj Mahal Hotel in Mumbai, right? And basically, I think that IIT Delhi and Taj Mahal Hotel jointly paid for the conference. Taj Mahal provided free rooms, and the conference paid for airfares or whatever it is. IIT paid for the airfares. But IIT complained because the Taj Hotel had the advantage because all of the guests were in their rooms. And so they were able to use the rooms to advertise themselves, a possibility which IIT didn't have. In any case, they were all in India, and Amartya Sen was a Nobel Prize winner. Was a Nobel Prize winner, and an Indian was present, as was Nash. And the Indian newspapers all printed an article about John Nash and said essentially nothing about Sen at all. And I think the reason why is that Nash had a movie made about him, A Beautiful Mind, and Sen didn't have such a movie. So I think it's time that we make a movie about Sen, and then maybe he'll be able to compete. So Alman was in India, and he knew that when you were buying things from a hawker, you had to bargain. And so he went to a hawker to buy an elephant, and the hawker asked 400 rupees. Alman knew that he had to bargain, and so he offered the hawker 200 rupees. The hawker immediately said yes, and Alman went home with that elephant for 200 rupees. Then he was told that particular elephant can be bought anywhere for 50 rupees, and you were cheated. So Alman was nonplussed by having been cheated, but he said, well, in any case, my time was worth more than 150 rupees. Okay. Now, a conflict in beliefs is not necessary for different evaluations of the same action. If Bob's set of beliefs Y is a superset of Anne's set X, then Bob accepts every belief that Anne has, and then the expected value of the words which satisfy X and those over the words which satisfy Y may end up having different signs. In other words, Bob believes everything that Anne does, and nonetheless there is a conflict. So here are three states of the world equally likely: cold, warm and sunny, warm and rainy. The utilities of a walk for both Anne and Bob are respectively -2, +5, -2. Anne knows that it's warm. Bob knows that it's warm and rainy. So all of Anne's beliefs are Bob's beliefs as well. The expected value of a walk as computed by N is 5 - 2 divided by 2 is 1.5 positive. As computed by Bob is -2. So Bob shares all of her beliefs, and nonetheless, Bob thinks it's not a good idea to go for a walk, and Anne thinks it's a good idea. Okay. Distance belief between beliefs. Suppose we are given actions even up to AM. Anne believes A and Bob believes B, but they have the same utilities. So let 7 up to CM be the payoffs calculated over the set of words satisfying A. D1 up to DM, the payoffs calculated over the set of the words satisfying B. Since there's the same utilities, the payoffs would be the same. Now we define the distance between A and B to be the maximum of C1 minus D1, comma, CM minus DM. In other words, so each action has utility calculated by Anne and a utility calculated by Bob. We take the absolute value of the differences, and the maximum of them is the distance between A and B. The distance is 0 if they are logically equivalent, and it's symmetric in A and B, so that DAB is DBA, and it satisfies the triangle inequality. To see the last, consider three formulas A, B, and C. Now, distance of AC is the maximum of certain differences. So let DAC equal CK minus FK, where F1 up to FM are the payoffs over the set of words satisfying C. Now, distance from A to C, absolute value of CK minus FK, which is less than or equal to CK minus DK plus DK minus FK. But I'm using the triangle inequality with the numbers, and that's less than or equal to DAB plus DBC. So we have a metric space defined by LD, where the L is the language of communication and D is the distance just defined. Now, the distance depends not only on AB, but also on sets of action pairs being considered. So let U be the set of action pairs and V be a subset of U. Let us denote the distances relative to U and V by DU AB and DV AB. Then if V is a subset of A, the distance according to V is less than the distance according to U. So the fewer the number of issues, the less the disagreement. Clearly, if Anne and Bob have the same beliefs and same utilities, then their values of payoffs of actions will be the same. So they'll agree on which actions are acceptable and which are Nash optimal. But if X is the beliefs of Anne and Y is the beliefs of Bob, and DXY is small, not 0, they may still agree on which pairs of actions are acceptable and which are Nash optimal. So let's say, for example, that Biden and Zelensky agree that Ukraine should have more weapons, but they may have different beliefs on other things. Or it may also happen that they agree on certain issues and disagree on some others. And in that case, it may happen that they'll agree on which movie to go to and disagree on which school to send their children to. And I'm sure that everyone here who is married has experienced this kind of a dispute with their spouse, because on some issues, there is no conflict, and on other issues, there's huge fights. So the conclusion is we've offered a framework in which beliefs affect the values of actions, and different beliefs by two agents may result in a disagreement over which actions are good. We define the notions of Pareto optimal and Nash optimal, and these notions are unambiguous when the beliefs are shared. They may be interpreted differently when the agents have different beliefs. We can also notice that when they have different beliefs, they still may agree on the utility value of one action pair AB and disagree on another pair CD. So issues having to do with knowledge and obligation have been addressed in 3.5. Stalnaker addresses the question of when we should believe another person. But our current treatment has some new ideas as far as I know. So we thank Neil Wang, Ali Khan, and Paul Peterson for useful comments. And now since I have a few minutes, let me say something about the references. So Anscombe Aumann, which is the first reference, to my knowledge, Anscombe Aumann are the first people who take up horse lotteries as opposed to roulette lotteries. I don't know this paper of David Grossi. John Nash, The Bargaining Problem. I would say, even if we hadn't found the Nash equilibrium, this is another paper which is absolutely brilliant. There's a paper by Eric, myself, and Eva Kogan, where we say that what you know can change your obligations. So say you're a doctor and there is a patient and there is somebody next door who is sick. You do not have an obligation unless you know that the person is sick. So your obligation increases when you acquire some knowledge. This paper by the three of us, Charles Tastimir is a former student of mine. Witzel is sort of a former student of mine because he got his degree from Amsterdam, and I was on his doctoral dissertation committee, but I was not his advisor. So we talk about how games will play differently depending on who knows what. One, Rui Robert, as I said, the director of ILLC, and Robert Stalnaker, he wrote an excellent paper about when people lie and when people can get away with it. So I'll say there's a brilliant paper on when will people lie and when can they get away. So in Stalnaker's example, Sally is applying for a position to a company, and I don't remember the name, so I'll just say to IBM. So Sally is applying for a position to IBM, and IBM has two positions, one which requires high qualifications and another which requires low qualifications. And they don't know whether Sally has high qualifications or low. So they rely on Sally to tell them. Now, one possibility is that if Sally has low ability and she's offered the high position, then she will not want that because she will be frustrated in that situation, not being able to perform. So if that is the case, then Sally's utilities and IBM utility coincide and IBM can trust her. The other possibility is where Sally believes that even if she has low ability and she gets a high position, she'll be able to manage, she likes a high salary and so on and so forth. And in that case, IBM cannot trust her. So the issue of when can you trust another person is discussed by Stalnaker to a great deal. You know, it's an absolutely brilliant paper. And I asked him whether he has followed up on it, and he said no. But considering that fake news is such a big thing now, I think everyone should read that paper. It tells you a lot about when you can believe something in which newspaper. So in general, I would say that when the New York Times says something which is pro-Republican, I believe it because the New York Times hates Republicans. When the New York Times says something good about Democrats, I take it with a grain of salt. With Fox News, it's the opposite. When Fox News says something good about Republicans, I'll take it with a grain of salt. And Fox News says something good about Democrats, then I believe it. And this actually was anticipated by Bertrand Russell. So Bertrand Russell said, and I would say that almost anything that has ever been said in philosophy in the second half of the 20th century was anticipated sometime by Russell. So Russell also anticipated the Gettier puzzle. So what Russell says is, if the Pope says that he believes in God, we need not believe him, because that's what he would say anyway as he's Pope. But if he says that he doesn't believe in God, we should believe him, because why would Pope say that unless it actually was true? So when you read somebody, then we have to ask the question, what is their slant? If they say something which is opposed to their slant, they're more reliable. If they say something which is in accordance with their slant, we should take it with a grain of salt. Okay, so I would say that actually all these papers are absolutely brilliant, including, of course, 4 and 5, in which I'm one of the authors. But I'm not saying it's as brilliant as the others, but I would say if you're going to read only 2 papers, I would read number 3 and number 7, and maybe also number 6. But all 7 are worth reading. So thank you very much for listening and for being patient, and I'm happy to answer any questions.